I'm going to go over the homework. This is WebAssign EM4 for Physics of the Universe. You only had one question, and it revolves around this electron energy diagram. So starting with A, question A asks us, electron drops from 4 to 2. So here's 4, plummets down to 2. Now, because the electron lost energy, it's going to emit light. How much energy did it lose? Well, final energy is negative 8.5. Initial energy is negative 1.2. The result is we lost 7.3 electron volts. That means you gain 7.3 electron volts of light energy. Now, that may be visible light. In fact, 7.3 electron volts, it's not visible light. It's too energetic. It would be ultraviolet. That's irrelevant, though. If we want to know what the frequency of that light is, E equals HF, 7.3 equals 4.14, E negative 15 times F. So why am I using the 4.14? Because I have the energy of light given to me in electron volts. So I'm going to use the electron volt second version of Planck's constant. I got 1.76 E15 hertz. That's the frequency of the light wave. Now B says, what's the wavelength of that light wave? All right, we're going to use C equals lambda F. C is the speed of light. That's 3E8. Set it equal to lambda times the F I just solved, 1.76 E15 hertz. So we'll do 3E8 divided by that frequency we just solved. I get 1.70 E negative 7 meters, or 170 nanometers. So that's definitely ultraviolet. Question C says an electron is at energy level n equals 3. So that's right here. And what's the minimum frequency required for an incoming light wave to eject? So in order to eject this, I have to gain 3.2 electron volts. That's essentially what the work function is at n equals 3, right here, 3.2. So in order to gain 3.2, that means my incoming light wave better have 3.2 electron volts. So 3.2 equals 4.14 E negative 15 F. Solve F. So go 3.2 divided by 4.14 E negative 15. Our frequency is 7.73 E14 hertz. D and E are by far the most complicated questions in this WebAssign. We're going to be focusing on the ground state, which is the lowest level right here at negative 13.6 electron volts. It tells us a particle of light has a given frequency, and it strikes an electron at the ground state. What's the kinetic energy of the electron? So that means the electron has been ejected. So we're trying to solve K. K equals HF minus the work function. Now, H is 4.14 E negative 15. The frequency was given to me as 3.49 E15. The work function is 13.6. What that means, what it literally means, 13.6, is in order for my electron to escape, it must get 13.6 electron volts of energy. Fortunately, 14.4 has been supplied by the light. So of the 14.4, we take away 13.6, and what's left over is 0.80 electron volts. That's how much energy we have for the light, for the electron, the kinetic energy of the electron. Now, E is asking, hey, you know the kinetic energy of the electron, tell me how fast it's going. Number one thing where I think people struggled with this is you have to convert. We need to convert because the mass of the electron is in kilograms, which depends on joules. So we're going to run a conversion, which is on your table of information. We'll go 0.8 times 1.6 E negative 19, and we get 1.28 E negative 19 joules. Now we're free to run K equals 1/2 mv squared. So 1.28 E negative 19. The mass of the electron is 9.11 E negative 31. How do I know that? Because I've been doing this for half my life. How would you know that? Because it's on your table of information. So I'm going to get 1.28 e negative 19 equals 4.56 e negative 31 v squared. So 1.28 e negative 19 divided by 4.56 e negative 31. I get 2.81 e11. And my final step is take the square root of that number. And I find out that the velocity of my electron is 530,103 meters per second, or 530,000 meters per second.